Okay, sir. So today we are going to start with I think lecture number 7. Can you tell me what happened in the past? Lecture number 6. What happened there? Then what did we do? What did we do in the last lecture? I obviously did not tell you the story of RRR. What happens in RRR? Obviously, that was not the point of discussion.
Absorption of X-ray, sir.
What of X-ray?
Absorption of X-ray.
Okay, I think last topic was absorption of X-ray, and I told you that it might not be a topic that requires a lot of attention. We only need to remember the formula that I gave you, and that is much more than enough that you will ever require if a question comes. Basically, we are done with X-rays. We are done with X-rays. Now, where do we head to? We head to the next topic, and I guess you already have the sheet for the next topic. What is the next topic known as? You have the sheet, right?
Nuclear physics.
Yes, the next topic is nuclear physics, and it also encompasses your chemistry ke kuch topics, because these two topics are very closely related to each other. X-rays were definitely not a part of chemistry. Yeah, maybe the discovery of X-ray was probably, you might find it in some books, but the entire topic was basically physics. Pay attention on this topic, because if a question does not come in physics from this, it can come from chemistry, and everything remains same. Nothing changes here, because this is all about equation, chemical equations, what happens, this mass number, atomic number, and all those things are going to come in this particular thing. That is why this may be a topic of chemistry as well. In some cases, what happens, when I was teaching in Pune, we never used to cover this topic in physics. It was covered by the chemistry teacher. Anyways, that is not how we are going to function over here. We will be covering this topic as it should be in physics. And from where do we start? What is the first heading? You all know it, already know it, right? You have definitely seen it from the sheet. What is the first heading?
Size of nucleus.
Yes, the first heading is definitely your radioactivity. I hope you understand the meaning of radioactivity. And to understand radioactivity, we'll have to understand something about the atom, which we already know. We'll just go through it very fast. I hope you know this. You may not have to write this. You already know this. Center of the atom is called the nucleus. You see the nucleus over here?
Yes, sir.
Nucleus has protons and neutrons. Together, they are known as
Nucleus.
nucleons. Nucleons. They are known as nucleons. They are inside the nucleus. They are known as nucleons. Will you remember this?
Okay, sir.
Okay, sir. Remember, the entire mass of the nucleus is supposed to be inside. The entire size of the entire mass of the atom is supposed to be inside the nucleus, because the mass of the proton and neutron, which are approximately same, are very high compared to the mass of the electrons. Do we know this?
Yes, sir.
So we say that the entire mass of the atom is inside the nucleus. Inside the nucleus, we have protons and neutrons. Protons are positively charged, neutrons are having no charge. Protons and neutrons together, they are known as nucleons, because they are inside the nucleus. The order of the size of the nucleus is again is in the order of Fermi meter, 10 to the power minus 15. Again, a straightforward question can come on this. You have to remember this. The order of the size of the atom is in the range of Armstrong units. Only protons and neutrons exist inside the nucleus. Electrons orbit. Now comes the three things that you must remember. Neutrons and protons together are known as nucleons. Will you remember this now?
Yes, sir.
What else? Now remember, don't get confused with this. Two things that are going to come. One is known as the atomic number. The other one is known as the mass number. What is atomic number?
Number of protons.
Yeah, it's not the number of electrons. You will say, sir, number of electrons and number of protons are same in the atom because the atom is electrically neutral. Why don't I call it as the number of electrons? Why do I call it as the number of protons as the atomic number? Why I can't just say, since both are equal, na? Electrons and protons, the number are equal. The atom is neutral. Why does the definition say that number of protons is atomic number denoted by Z? Remember, this letter Z is for atomic number. Why the number of protons is atomic number, and why we don't call it in terms of electron? Your answer, fatafa, give me. I don't have the time of the entire universe. Why not the number of electrons? Do you have an answer? Yes or no? Yes is 1, no is 0. Binary. 1 or 0? 1 or 0? Fast, fast. Do you know the answer? 1, yes. 0, no. Binary code. Tell me.
1, sir.
1, sir. Yes, sir. So you know the answer, sir. What is the answer, sir? Tell me the answer, sir, then. Fatapat, sir. Do you know the answer? You have to tell me the answer. What is the answer? Why we do not call it by the number of electrons? We don't call it by the number of electrons because number of electrons can be changed. I can have an electron taken out from the outermost shell, and I can have an electron added to the outermost shell. By doing that, I will change the number of electrons. But does that change the atom? No. The atom still remains atom, the same atom. I can add an electron in hydrogen outermost shell. I can remove an electron from the outermost shell of hydrogen atom. Still remains hydrogen. I do not change the type of the element that I was dealing with. But if I change the number of protons, I change the atom itself. It no longer remains the same atom. The atom changes, and therefore atom is identified by the number of protons and by not the number of electrons. Am I clear?
Yes, sir.
Yes, sir. No, sir. Then, sir, the total number of nucleons. When I say nucleons, what do I mean?
Neutrons plus protons.
Total number of neutrons plus protons. If I add these two, I will get the mass number A. Remember, mass number and atomic number, and also remember how I represent the atom. The atom is represented like this. X is the symbol of the atom. Z comes here, A comes here, or it may be written like this. This is what you have to write. Z, the atomic number, is written on the lower side, either on the right hand side or the left hand side. The mass number is written on the top right hand side. Mass number is the total number of nucleons, whereas Z, remember, is not the number of electrons, is the number of protons. We understand this?
Yes, sir.
A minute to write it, sir. We'll have to note this. What is atomic number? What is mass number? Atomic number is denoted by the letter Z. You may say, sir, atomic number, it starts from A. I should write A for that. No, it's Z. That's a convention. We follow it. Mass number is written by A. You say, sir, mass number starts from M. We should write it as M. But that is not how it is written. So remember, that is why you might get confused. Whenever you see A, you might have a doubt. Or A stands for atomic number. No, bacha. A does not stand for atomic number. A stands for the mass number. Are you getting my point?
Yes, sir.
Yes, sir. So remember it, sir. It should not be confusing, sir, because if you confuse atomic number and mass number, you are gone. No one is going to save you. Shall I proceed further?
Yes, sir.
Then, sir, we have to understand what are we studying here. We are studying radioactivity. Now, what happens in radioactivity, we have to understand how the nucleus is held together. Now, there are three types of forces, or I should say four types of forces acting over here. The first one is the gravitational force between the particles. This gravitational force exists between two protons. It exists between two electrons. It exists between two neutrons. It also exists between proton and neutron. It also exists between neutron and electron. It also exists between proton and electron. Do we understand this? It exists between any two bodies which are having masses. Yes or no?
Yes, sir.
But what do we see? That gravitational force is a very small force compared to electrostatic force. So because of this gravitational force, this atom cannot exist, because inside the atom, inside the nucleus, we have very strong repulsive forces between the proton and proton. Do we understand this? Inside
Yes,
the
sir.
nucleus, we have protons and neutrons. Neutrons do not have any charge. Protons have positive charge. So two protons are going to repel each other. They're going to throw each other away.
Yes, sir.
Gravitational force is not strong enough to hold this. If that is the case, the gravitational force is not strong enough, and electrostatic force is going to repel them away, there must be some other force which is holding the nucleus together. There must be some other force which is holding the nucleus together. Do you know what that force is known as? Which is holding the nucleus together? It is known as
Nuclear
the
force.
strong nuclear force. There are two types of nuclear forces: strong nuclear forces and weak nuclear forces. Right now, we are concerned about the strong nuclear forces. These strong nuclear forces exist between the nucleons. It exists between proton and proton. It exists between proton and neutron, and it also exists between neutron and neutron. So it exists between any two pair of the nucleons. This is very, very strong compared to the electrostatic force. In fact, this strong nuclear force, the name tells us that this is the strongest force in nature. Strong nuclear force is the strongest force in nature. But the problem with this force is it acts on a very small scale. On a small scale, I mean, on very small distances only it is applicable. Inside the atom, the distances are very small. Only there it is applicable. But inside the atom, at very small distances, this is the strongest force in the universe. Do we understand this?
Yes, sir.
And therefore, there is a lot of energy, because this force creates energy. If I somehow break this nucleus, which we are going to break in this chapter, this large amount of energy will be released, and that is what we call nuclear bomb, fusion bomb, fusion bomb. Have you heard about Hiroshima and Nagasaki? The destruction that this bomb, and right now a nuclear war is waiting to happen between two countries. The problem with this is, if you break this nucleus, very large amount of energy is released in a very short time, and that causes mass destruction. And that is why this is the strongest force in nature. Do we understand this?
Yes, sir.
Now, you must remember some points about this strong nuclear force. Again, these points may come as some points in your exam, so you just have to read it and remember it. The first point, it is the most it is the strongest force in nature. Do we understand this?
Yes, sir.
It only acts between nucleons, so two electrons cannot have this nuclear force. We understand this?
Yes, sir.
It is of very short range. Only inside the nucleus it can happen. It depends upon distance. A very small variation in distance will cause a very large change in the value. Is it independent of charge? Proton, between two protons it will happen, between two nucleons it will happen. It does not depend on charge. Does not depend on spin, whether it is spinning up or spinning down. You know that from chemistry, spin up, spin down. One electron will be like this, the other one will be like this. It does not depend on the spin. It is not a central force. Central force acts between the two particles along the line joining these particles. Electrostatic force is the central force. Do we understand this?
Yes, sir.
but this is not a central force. Will you remember all these points? Yes or no?
Yes, sir.
So this is not a central force. And remember, the most important point is coming in the last two lines. First of all, it is not a central force. Electrostatic and gravitational force are central force, but nuclear force depends on spin. It depends on the spin. I said it does not depend on spin. A slip of tongue. It does not. It depends on spin, and also it is not a central force. Do you understand this?
Yes, sir.
Now remember, it can be attractive as well as repulsive. All these things are for your information. This can come in the question straight away. When it is attractive, the distance is 1 fermi-meter. When it is repulsive, the distance is less than 0.5 fermi-meter. Do we understand this?
Yes,
So
sir.
there could be a question where it says strong nuclear force. It is always attractive. It is always repulsive. Both. None. So you have the answer for that thing. Do we understand this?
Yes, sir.
Now, the next thing that we are going to study is radioactivity. Have you heard about the term radioactivity? You might have heard, you might have done it in chemistry, yes or no?
It has not completed, sir.
Not done?
Yes, sir.
Okay. What do you mean by radioactivity? What do you mean by radioactivity? Heard this term or not? First of all, tell me that. Have you heard this term or not, radioactivity?
Yes, sir.
Yes. So, from your understanding, what do you mean by the term radioactivity?
Emission of energy in the
Yes, beta? Emission of?
energy.
Emission of energy. Okay. Why this emission of energy occurs? We will be doing this in great details when we get onto that nuclear physics wala chapter, but radioactivity we are doing before that. You must understand, and I'm going to show this diagram, which is from the next topic. I've shown you a diagram. Now, you must understand that nucleus of an atom. There is a strong nuclear force which is trying to hold this. You understand this? The strong nuclear force is trying to hold this
Yes, sir. Yes, sir.
nucleus together, and the repulsive forces, the electrostatic forces, are trying to break it apart. Yes or no?
Yes, sir.
Now, the energy you require to break this nucleus, or the energy which is required to hold it together, you call it binding energy. We will be doing this term binding energy in great detail, but we call this term as binding energy. Do you see this term binding energy?
Yes, sir.
So this is the energy that is holding, in short, it is holding your nucleus together. Now, if this energy is very less, as you can see here, the energy is less. Do you see this? Energy is very less. Yes or no?
Yes, sir.
At this point, this energy, which is per
Is
nucleon,
maximum.
it is very high. Now, when this energy is very high, which is the case of this particular isotope of iron, Fe5626, have you heard about this isotope, Fe5626? This is the most stable nucleus
Yes, sir.
that we know about. This is the most stable nucleus that we know about. That means this is very hard to break. This is very hard to break. Now, if I go higher up, if I increase the atomic number or the mass number, here you can see mass number is increasing. Do you see this?
Yes, sir. It is increasing.
You can see this energy is decreasing. Yes or no?
Yes, sir.
Well, now we have our answers. Now, every nucleus, for everyone, what is our first desire? Always. Everyone wants to be stable. Yes or no? We want to be stable in our life. You must have heard this term philosophically. Be stable in your life.
Yes,
Don't
sir.
wander here and there. Don't do anything abruptly. Be stable. Get a decent job. Become a doctor. Become a MD. Become a DM. Have a stable life. Yes or no?
Yes, sir.
Every nucleus also wants the same thing. It also wants to be stable. But as you can see from this diagram, and you might not understand this diagram, we'll again come back to this diagram, maybe 2 class from now. If you see from this diagram, what happens when the nucleus becomes very big, it becomes less what? It becomes less stable. Do we understand this?
Yes, sir.
When the nucleus becomes very large, it becomes less stable. Now, if I become less stable, I am very big and I am very stable and I am very unstable, what will I do? This larger nucleus, and I'm just changing the color of the pen, I'm making it blue. This larger nucleus, you can see this larger nucleus here,
Yes, sir.
is going to break into smaller nuclei. Do we understand this?
Yes, sir. Separation.
Larger thing, larger nucleus breaking up into smaller ones, because the smaller ones are more stable compared to this larger one. We understand this?
Yes, sir.
This is known as fission, and right now we are going to study this fission. We have an unstable nucleus. It breaks up into other nuclei. You can call this as radioactivity or fission. Do we understand this?
Yes, sir.
We call this one as the mother. This is the mother, and these two becomes their daughter. Do we understand this?
Yes, sir.
This is nuclear fission, breaking, fission, tutna, fission. You look on the left hand side. On the left hand side, what do you see? I use a different color. I use the green color. On the left hand side, what do you see? You see two smaller nuclei
Fusion. Combining, sir. Fusion.
combining to make a larger nucleus, because here on the left hand side, when the nucleus are very small nucleus or nuclei are also unstable, so they want to become larger, because larger nucleus is more stable. This is known as nuclear fusion. Do we understand this?
Yes, sir.
The most of the nuclear energy that we are getting now is from which process? Fission or fusion? Fission or fusion? Fission or fusion? This nuclear power plants, this atomic bomb, are we creating it by fission or fusion? Are we fusing things, or are we making them smaller? Everything that we are doing right now is fission. A larger nucleus is breaking into smaller nucleus, but the problem with this thing is whatever energy is given out is in the form of radioactive energy. It has radioactive components, and that is why this is very harmful. Do we understand this?
Yes, sir.
On the left hand side, the green one, two smaller nuclei combining to get a bigger nucleus. This is not radioactive. The emissions are not harmful, and therefore this energy is much more safe, much more environment friendly. Two hydrogen becoming helium, two helium becoming higher. This is very safe energy, but the problem with this energy is that it takes place at very high temperatures. You can have this fusion, but this fusion happens at very high temperatures. You know where this fusion happens? What is the source? Which body, which heavenly body gets its energy from fusion? Your sun. Inside sun, the temperatures are very high and fusion is happening. Two hydrogen are becoming helium, and it is releasing tremendous amount of energy, and that energy is radiated by earth, radiated by sun towards earth, and we are trying to make this fusion happen, because this fusion is not radioactive, it is clean energy. Do we understand this?
Yes, sir.
So basically, larger nuclei are less stable and they are going to break up on their own. Sometimes they're going to break up into smaller nucleus. You can call this process as fission, or you can also call this process as radioactivity. Do we understand this? And as
Yes,
soon as you
sir.
hear the term radioactive, you understand that this radiation which is given is pretty harmful for human beings. Yes or no?
Yes, sir. It's
A
harmful.
nuclear bomb, when it explodes, it might not cause that much of damage. Most of the damage is caused by the radiation that this thing emits. That we understand this, yes or no?
Yes, sir.
So that is the problem with this fission. That is the problem with this fission. It releases radioactive substances and radiation which are very harmful, and it will remain for generations in the human race. Hiroshima and Nagasaki, still babies have deformities because of this radioactive radiation. Do we understand this?
Yes,
This is
sir.
known as radioactivity. So what is radioactivity? Spontaneous. You have to write this. Spontaneous emission. Spontaneous. It just happens spontaneously. All of a sudden, ekdam se. Spontaneous emission of radiation from the nucleus is known as radioactivity, and the substance showing this property are known as radioactive substance. Do we understand this?
Yes, sir.
Who is going to show this radioactivity? Only unstable nuclei. Do we understand this stability and instability? Yes or no?
Yes, sir.
A particular nuclide, it happens inside the nucleus, so we call it nuclide, can radiate only a particular type of radiation according to its requirement of stability. So it cannot emit all types of radiation. A bigger nucleus will become smaller nucleus. It will emit a special type of radiation. Do we understand this? From there, you can find out which nucleus has decayed. Yes or no?
Yes, sir.
This event where was discovered by Becquerel, and then someone else came and gave us very nice things on this, and she got a Nobel as well. You know this, right?
Right, sir.
The husband-wife pair of Marie Curie and Pierre Curie, they got the Nobel for this. Madam Marie Curie got Nobel once more. The only person in the history, female also, to get two Nobels, and that too in two different streams, one in physics and one in chemistry. Do we know this? Yes or no?
Yes, sir.
I'll give you a minute to note this down. Have you written
Done.
this?
Yes, sir. Done.
Then, sir, this, sir, Rutherford experiment. You might have heard about this Rutherford experiment. Yes or no?
Yes, sir.
We have this radioactive substance. We have kept it in a lead box. Why we have kept it in a lead box? Because it absorbs radiation. Do we know this? Yes or no?
Yes, sir.
And this is a small hole here. It is looking very large, but this is very small. So you can see three types of radiations are emitted. One type of radiation which are deflected towards negative plate. They are known as alpha rays. Do we see these alpha rays?
Yes, sir.
Do we see these alpha rays? Yes or no?
Yes, sir.
Then there is something which is deflecting towards positive plate, which is known as the beta rays. Do we see this?
Yes, sir.
Then we have an undeflected radiation, which is known as the gamma rays. So three types
Yes,
of radiations
sir.
are emitted. Alpha rays, they are made up of positively charged particles. Beta rays, negatively charged particle. Gamma rays, electromagnetic wave of photon. It does not have any charge. That's why it is undeflected. We understand this?
Yes, sir.
So this is what you will write in short. Alpha is consisting of positive particles deflected towards negative plate. Beta consists of negative particles deflected towards positive plate. Gamma is electromagnetic radiation, and we have an entire table coming up. We have an entire table coming up for these radiation, then you will have to remember everything in this table. Have you noted this down, bacha?
Done, sir.
Then you have this table, and everything in this table has to be memorized. What happens with alpha particles, what happens with beta particles, and what happens with gamma rays. Number one, this is helium nucleus. You take out the 2 electrons from the outer shell, and whatever remains is helium nucleus. It only has positive charge. This is your alpha particle. Yes or no?
Yes, sir.
So beta particle is nothing but electrons. They are denoted by B minus, beta minus, or E minus, whatever you
Yes,
feel
sir.
it.
Negative charge.
And this is photons. You understand this?
Yes, sir. Neutral.
Then you have the charge, twice the charge of proton, charge of an
Twice.
electron. This is neutral. Yes or no?
Yes, sir.
Mass, 4 times the mass of proton. We understand this. 4 nucleons are there.
Yes,
This
sir.
is the rest mass of electron, mass of an electron. Here the rest mass is 0. Remember, photon's mass is 0. We understand this.
Yes, sir.
I hope everyone is following the discussion and not sitting there ideal. Yes or no?
Yes, sir.
You are noting it down as well as you are trying to memorize it. Yes or no?
Yes, sir.
Then, sir, this speed. No one is going to ask you speed of these two. Probably they might only ask you the speed of this one. Do you know that this is the gamma particles, which are photons, will have speed of light? Yes or no?
Yes, sir.
Their kinetic energy is in mega electron volt. Do we understand mega electron volt? 10 to the power 6 electron volts. Yes or no?
Yes, sir.
Okay, the energy spectrum, you may not remember this. This might not be asked. So we can leave this. I'm just going to cover the important points that would be asked in your examination. Ionization. Who is having the highest ionization power? You have to remember this series. Alpha is having the highest ionization power, then beta, then gamma. Will you remember this?
Yes, sir.
The penetrating power, the energy is the reverse of it. So if you remember any one of these, you can do the reverse and make the other one on similar lines. Do we understand this?
Yes, sir.
Deflection of electromagnetic field. This will deflect toward the negative plate. This will deflect toward the positive plate, and this will not deflect. We understand this? We understand this, bacha?
Yes, sir.
Okay, sir. Then we will understand these decays one by one. Alpha decay, beta decay, and gamma decay. And that is all about radioactivity that you have to understand. Do we get this, bacha? First one in this line is alpha decay. What is an alpha particle? What is an alpha particle? We have already seen an alpha particle. Yes or no? An
Yes,
alpha
sir.
particle.
Positive charge.
Alpha particle is basically helium nucleus. Don't say positive charge. Say it is helium nucleus. Yes or no?
Yes, sir.
So some nuclei which are unstable is going to emit alpha particles. Yes or no?
Yes, sir.
Why they are going to emit alpha particles? Because they are highly unstable. Got this? By emitting these alpha particles, what will happen? They will become more
Stable.
more stable, and that is why they emit these alpha particles. Don't have to remember the entire thing that is written here. You just have to remember this equation of alpha decay. What happens when an alpha particle decay? So write the heading equation of alpha particle decay. That is the only thing that we are concerned about right now. Do we understand this?
Yes, sir.
And what is the equation? Can you see the equation, sir?
Yes, sir.
What is the equation, sir? Tell me, sir. It comes on the bigger screen like this. What is this, gentlemen? This is your parent nucleus. Remember, whenever we're talking about radioactivity or this chapter, nuclear physics, we are concerned by the nucleus. We're not concerned by the electrons which are moving around. Do we understand this?
Yes, sir.
This is the parent nucleus. We got this?
Yes, sir.
What do we have here is the daughter nuclei. Do we understand this?
Yes, sir.
And then we have a helium nucleus jumping out. Do we understand this?
Yes, sir.
Helium nucleus has a mass number of 4 and atomic number of 2. Do we understand this?
Yes, sir.
The parent has atomic mass number A and atomic number Z. Do we see this?
Yes, sir.
What will the daughter have? Daughter will only have A minus 4 as the mass number and Z minus 2, because everything has to be balanced. Balanced chemical equation. This is something like a chemical equation. It has to be balanced. Mass number on this side should be equal to mass number on this side. Atomic number on this side should be equal to atomic number on this side. Charge on this side should be equal to charge on this side. Do we understand this?
Yes, sir.
That's it. That's what we get. Clear?
Clear, sir.
And this daughter nucleus will be more stable compared to the parent nuclei. Have you written this equation? This is the only equation that we have to understand here. Yes or no?
Yes, sir.
Please note it down.
Done, sir.
This is what we call as the alpha decay. Do we understand this?
Yes, sir.
Then the next decay will be known as beta decay. Yes or no?
Yes, sir.
Now this beta decay, as you can see, is of two types. One is known as negative beta decay, and the other one is known as positive beta decay. You understand this?
Yes, sir.
Okay. Right now we are going to do negative beta decay. Now it has been explained in great detail here, but we don't need that great detail. We only need this. After writing negative beta decay, we only need this equation, and I am going to enhance this equation. We don't have to read the entire thing because it will be of no use. The only thing you must remember that this negative beta decay happens because of weak nuclear force or weak nuclear interaction, which I have highlighted. Do you see the highlighted part? Weak nuclear interaction. Why this negative beta decay happens? It happens because of
Weak nuclear interaction.
weak nuclear interaction. Weak nuclear interaction. This is what you must remember. And then you remember this equation, which I am going to get you in bold. And what happens here? What happens here? Can anyone tell me what happens here? I'm just taking out this yellow part. What happens here is one neutron inside the nucleus is getting converted into what? Neutron is having no charge. It's getting converted into proton. Proton has a positive charge. Yes or no?
Yes, sir.
Then it emits a beta particle, which is nothing but an electron. It has negative charge. So one positive, one negative becomes neutral. Yes or no?
Yes, sir.
And it also emits one new particle. This new particle is written like this, and this new particle is known as anti-neutrino. Do we understand this?
Yes, sir.
So this is the equation that you have to remember for negative beta particle. Do we understand this, my bacha?
Yes, sir.
Okay, have you written this equation? Have you written this equation, my dear friends?
Yes, sir.
Bacha, will you remember this? What are the things that you have to remember in beta decay? That this happens because of weak nuclear interaction. Yes or no?
Yes, sir.
And here what happens? One neutron becomes one neutron becomes what?
Proton plus beta particle.
Who will say antineutrino? Who will say antineutrino? Who will say antineutrino? There is a new particle which is produced, which is known as antineutrino. Will you remember this?
Yes, sir.
Now, if I write the next heading would be your decay equation. I will write it in terms of the decay equation. Now, look at very closely to this decay equation. Decay equation. You have this. What is this? This is the parent nucleus. Yes or no?
Yes, sir.
This is the daughter nucleus.
Yes, sir.
Now you see the relation between the parent and the daughter. A remains A because protons becomes a neutron. Mass number does not change. Do we understand this?
Yes, sir.
But look at the atomic number. Is the atomic number changing?
Yes, sir.
Why is it changing? Why is it changing? Because I have one proton produced. Yes or no?
Yes, sir.
Then I have this beta particle coming out, which is an electron, and I have this antineutrino. Do we understand this?
Yes, sir.
This daughter nucleus is an isobar. It has the same mass number. Do we remember this?
Yes, sir.
These are the things that you may have to remember. After beta decay, N by P ratio, neutron become less, protons become more. So N by P ratio decays. Yes or no?
Yes, sir. Decreases.
And we always have one anti-neutrino beta particle, negative beta particle, electron coming out, and one in anti-neutrino together with it. Do we understand this?
Yes, sir.
Can I have some raised hand from everyone in the class that we understand this, sir, and something good has come out of this? You understand both the equation, how they are related? The first equation tells us what is happening. The second equation tells us how it is going to come in the examination hall. Can I have some raised hand that we understand this?
Yes, sir.
Girls on the left, right, everyone. Are we there in the same class? Yes, same universe. This is a good universe to live, beta. We might have some stupid people in this universe, but overall, this is a good universe to live. F is equal to ma. This is a very good nucleus. Very good universe to live in. Now, since we are done with negative beta decay, what should be the next? What should be the next heading? Yes, sir. Tell me, sir. What should be the next heading? You are again looking at the notes, but okay. Even if from the notes you can tell me. अरे यार नेगेटिव बीटा के बाद क्या आएगा?
Positive.
Why are people throwing stuff here and there? Don't throw stuff. Okay. After negative comes positive, and here is the positive beta decay. Do we see positive beta decay? In positive beta decay, everything is becoming ulta. Do you see ulta here? Do we see ulta here? Ulta happening here?
हाँ sir.
हाँ sir, tell me sir, what is happening sir? अरे sir, जल्दी sir. You don't have the time of the entire universe sir. Okay. First thing first. Why this is happening? This is happening because of whether it's a positive beta decay or negative beta decay. Why is it happening? It is happening because of
Weak nuclear interaction.
never forget this in your entire life. Weak nuclear interaction. This is the only way. This is the only time when this weak nuclear interaction is happening. What is happening in this positive beta decay? Tell me, bacha. It's right there on your screens. And you see the difference in the symbols and you see the difference in the language. What is happening here? Tell me.
A proton giving a neutron plus a beta particle plus a new particle.
Yes, this positive beta particle is known as positron. We can call it the ulta of electron.
Yes,
It
sir.
has the
Positive
same
charge.
mass as that of electron, but the charge is opposite. Do we understand this?
Yes, sir.
Yes, sir. So here, sir, everything is ulta, sir. Here my proton is getting converted into neutron, and therefore a positron or positive beta particle is going out with another new particle which is known as neutrino. Do we understand this? Can I have some raise hand if we understand this?
Yes, sir.
Yes, sir. Have you written this equation, sir? This has to go in your notebooks, not in your sheet that you have. It's already there in your sheet. The sheet is already given to you. You understand this? Yes or no?
Yes, sir.
Yes, sir. No, sir. Then, sir, we write the decay equation, sir. So the next heading is the decay equation. Decay equation, and no prizes for guessing what is going to happen in this decay equation. As you can see, the decay equation is right there on your screens. This is your parent. Yes or no?
Eh,
This is your daughter. Yes or no?
Yes, sir.
What do you see about the mass number? Is it changing?
No, sir.
Because proton converting into neutron or neutron converting into proton, mass number remains same. But what do you see here? The atomic number decreasing by 1. Yes or no?
Yes, sir. Decreasing.
Positron is getting out. Neutrino is getting out. Atomic mass number is unchanged. Atomic number is reduced. This is
By
also an
1.
isobar at N by P ratio here. Is it increasing or decreasing?
Increases, sir.
It increases because neutrons become more and proton becomes less. Do we understand this?
Yes, sir.
Please, sir, note it, sir. I'll give you a minute, sir. That should be enough for you, sir, to note it down, sir. This has to be in your notebooks.
Okay, sir.
Okay, sir. Done, sir.
Done, sir.
Done, sir. Then, sir, this, sir. Again, these are points that you must remember. They would come into examination hall as straightforward points. The first point are these are both chargeless. What are these? Neutrino and
And
antineutrino.
antineutrino. Both are
They are both chargeless. They have zero less mass, same as photons. They both are energized particles. They have energy. They have spin quantum number. You understand spin quantum number? Spin angular momentum.
Yes, sir.
Similar to electron. They were suggested by Pauli's exclusion principle. Do we remember this? We have to remember this. There is no other way out. Do we understand this?
Yes, sir.
Very good, sir. Then, sir, this, sir. We are done with alpha decay. We are done with beta decay. Beta decay was of two types.
The positive and negative.
Positive and negative. What remains now?
Gamma.
Huh? What? Alpha हो गया, beta हो गया. Then what remains is gamma decay. And here comes my gamma, gentlemen. Gamma. Now what happens in this gamma decay? Now this is a sort of an intermediate decay. Now what is this intermediate decay? If I try to make you understand, see, this is the parent nucleus, tongue. This is the daughter nucleus, tongue. This parent nucleus will undergo alpha decay or beta decay. Now that will give rise to a daughter nucleus. Now sometimes this daughter nucleus that you get, it is not in the ground state. Now you must remember all this ground state and excited state from the atom wall chapter. Do we remember this?
Yes, sir.
When electron goes higher up in the orbit, it becomes excited. When it comes lower down, it releases energy. We remember this, yes or no?
Yes, sir.
So sometimes in this alpha or beta decay, when the nucleus is undergoing alpha decay or beta decay, sometimes the nucleus which is formed for the daughter, it is at an excited stage. It is at an excited state. No one remains at an excited state. We can remain at an excited state, but again, we have to come to a ground state. Yes or no? Because ground state is more stable. Yes or no?
Yes, sir.
As you can see here, this star means that it is at the excited state. Do you see this star?
Yes, sir.
So what is going to happen here is that this star tells us that this nucleus that has been formed is at an excited state. What will happen that it will try to come back to its ground state. So this star is the excited state. This is the ground state, and it will give out gamma photons. These are gamma radiations, which are electromagnetic radiations. The energy of these radiations is H multiplied by F. Do we understand this?
Yes, sir.
Here, as you can see, the nucleus remains same. There is no change in mass number. There is no change in atomic number. It's just nucleus has more energy, excited state. It comes back to the ground state by emitting some photons or gamma radiation. Do we understand this?
Yes, sir.
This is the equation that you have to remember this. And this is the explanation that is going to come. And this is what we see here. Tan. Equation of gamma decay. Asterisk shows excited nucleus. I hope you understand this. Gamma radiation or emission does not change the nucleus. There is no change in that mass number and the atomic number. Do we understand this? Yes or no?
Yes, sir.
Yes, sir. Then are we ready for the question, sir?
Okay, sir.
So this is your question. You also have your sheet. Example number 1. Thorium 23490 gives falana, gives something. Then I have X, BA. Then it gives something. Then I have Y, DC. Then it gives something. Some particle P. And it gets a thorium 23090. Find A, B, C, D, and then find the particle P. What is that particle? Is it alpha decay, beta decay, gamma decay? Do we understand this? Yes or no?
Yes, sir.
Yes, sir. Then, sir, the time is yours, sir. It starts now, sir. Please tell me the answer, sir. You'll have a minute to minute, as always. Anyone with any answer? Yes, sir. No, sir.
Sir, XB is 23088.
23088. So B is 230. A is 88. Yes. What about the next one, bacha?
23089.
23089. That is correct. So your D is 230. C is 89. Absolutely correct. What about the last particle P? What is that P?
D part
Negative beta or positive beta, bacha?
negative beta.
Negative beta. That is absolutely correct. And these are the answers. I hope all of you have done this. Yes or no? Please tell me by raising your
sir.
hands. Yes, sir. No, sir.
Yes, sir.
Everyone done, sir?
Yes, sir.
This is how questions come in your examination hall, and this is how you have to tackle them. It is straightforward, very simple. Everyone has seen this, yes or no?
Yes, sir.
These are the type of questions you will have. And this is the next question that I am going to show you. This might require a bit more work, but again, if you can do this, I would be pretty glad. And the question comes right now. Thorium 23490 gives N alpha, N dash beta. It becomes bismuth 21483. Find the value of N, which is the number of alpha particles, and N dash, which is the number of beta particles. Your time starts now. And you have minute to minute. Are we solving the question or sitting?
Solving, sir.
Solving, sir. I see you sitting, sir, which is not a good sign, sir. If you sit now, you will have to sit out of the exam as well. Trust me on this. So how do you find the value of N and N dash? Shall I help
Alpha
you?
is 5, sir.
N is 5. Well done. Alpha is 5. And what about N dash? N is 5. That is correct. Yes, yes, that is correct. Okay, I will help you out. Now, how do I find the value of N? To get the value of N, which is the number of alpha particles, is very simple. The only way you can change the mass number, remember the original mass number is 234, yes or no?
Yes, sir.
And the final mass number is 214. The only way you can change mass number is by emitting alpha particles, yes or no?
Yes, sir.
When you emit one alpha particle, how much does the mass number change? It changes by 4, yes or no?
Yes, sir.
Here it is changing by how much? 20, yes or no?
20 by 4.
20 divided by 4. So I have the number of alpha particles. The number of alpha particles would be 5. Do we understand this? Can I have some raised hands? Everybody in the class, girls, especially. Yes. Now, once I have the number of alpha particles, one alpha particle will reduce the mass number by 4, but increase the atomic number by 2. Yes or no?
Yes, sir. Decreases by 2.
Sorry, decreases the atomic number by 2. Yes or no?
Yes, sir.
So the original atomic number I think is 90. Yes or no?
Yes, sir.
And it will decrease it by 5 into 2. So it will decrease it by 10. So the new atomic number becomes 80. The original was 83. The new is, the original was 90 and the new is coming as 80. But it cannot be 80. It is actually 83. Yes or no? So someone has to raise it. Or if it's getting too confusing, you can remember this formula. Number of beta particles will be atomic number final minus atomic number initial minus 2 times the number of alpha particles. If you can remember this, you'll get the answer straight away, or you can apply some logic. The final was 90. The initial was 90. If I emit 5 alpha particles, the final would be 80. But the final is not 80. Final is 83. So you must emit 3 beta particles. Do we get this, or is it getting confusing?
Okay, sir. Yes, sir.
When I emit alpha particles, mass number goes down by 4, atomic number goes down by 2.
Yes, sir.
When I emit beta particle, negative beta particle, atomic number goes up by 1. When I emit positive beta particle, atomic number goes down by 1. Do we understand this?
Yes, sir.
If you can remember this, my dear friends, we are done with this part. Do we understand this?
Yes, sir.
Okay, then we can have this small thing. Sometimes we are going to bombard a parent nucleus with a particle. This X is the parent nucleus, this A is the particle. You will have a daughter nucleus and you have an emitted particle. They might ask you what is the value of this. What you have to remember is all nuclear reaction follow conservation of the number of nucleons and charge. Do we remember this?
Yes, sir.
As well as energy and mass conservation, linear and angular momentum conservation. If you just remember this thing, you can solve any question that comes in the examination hall. Do we understand this? You have to conserve mass number, you have to conserve atomic number, you have to conserve the charge. Do we understand this? Yes or no?
Sir, once again.
Yes, sir?
Once again, repeat, sir.
You have to, in any reaction, you have to conserve atomic number, you have to conserve mass number, and you have to conserve charge. Mass number on this side should be same as mass number on that side. Atomic number on this side should be same as atomic number on the other side. Charge on this side should be same as charge on the other side. Do you understand this?
Yes, sir.
Then we have the next heading. I hope everyone is following me. Yes or no? I'll give you a minute since we have done so many things today. I'll give you a minute to go back and see what we have done. We have done 3 types of decay. Alpha decay, mass number changes by 4, atomic number decreases by 2. Beta negative decay, atomic number falls by 1. Beta positive decay, atomic number gets up by 1. Gamma decay, nothing changes. The nucleus is in a excited state. It comes to a ground state. Do you have any doubts on this? I give you 1 minute. Yes or no?
Completed, sir.
Shall we move ahead?
Yes, sir.
Now we come into your main heading, and the main heading was radioactivity. Now, what is going to happen in radioactivity? Simply, I will have a nucleus. This nucleus is not going to be stable. It is going to decay. It might decay by alpha decay, it might decay by beta decay, or it might, in somewhere in between, it might give you a gamma particle as well. We have seen the chemical reactions for that. Don't call it chemical reaction. That's not a chemical process. We have seen the nuclear reactions. Those were the nuclear reactions. Do we understand this?
Yes, sir.
We have seen the nuclear reaction. Now what we are going to do is, how is it going to decay? What is the rate? And then comes the legendary Rutherford and the Soddy's law. And what does this Soddy's law say? Please write this, understand this. At any instant, the rate of decay of an active nuclei is directly proportional to the number of active nuclei. Do we understand this? If I write the rate of the decay is dN by dt, it is directly proportional to the number of nuclei. Do we understand this?
Yes, sir.
Why I write a negative sign before this? Because the rate is negative. So I make two negatives, it becomes positive. Getting my point?
Yes, sir.
This is what I call Rutherford's law. Minus dn by dt is directly proportional to n. Do we see this in the blocks? Or
sir.
I can write it as dn by dt will be, or minus dn by dt will be equal to lambda n. Do we understand this?
Yes, sir.
Where lambda is a constant and this constant is known as the decay constant. We understand this? This constant is known as the decay constant. It only depends on the nature of the substance. If it is thorium, it will be different. If it is uranium, it will be different. If it is radium, it will be different. Do you understand this? Can I have some reason I understand this? Everyone in the class, I don't see your hands. That is horrifying. Do you understand this? Have we written this? This has to come in your notes.
Yes, sir.
Yes, sir. No, sir. Then, sir. What, sir? I can go ahead
Sir, repeat it once again, sir.
and I can write it like this. So what I had was, you just have to remember the symbol minus dn by dt. It's a derivative. Minus dn by dt is equal to lambda n. Now, from here on, it is simply maths. From here on, it is simply maths. Minus dn by dt is the rate at which the nucleus is decaying. Lambda is the decay constant. N is the number of active nuclei. We understand this?
Yes, sir.
So I can write it like this. I have taken n on this side and it becomes dn by n is equal to minus lambda dt. Is it okay? After that, what we are going to do? We are going to use maths, which is not a part of your curriculum. So we will not go into it. You will just write this step after that step. And then we will write the final result. And what is the final result? The final result will look something like this. And I want you to remember all the three different variations of the same equation. I want to remember the three variation of the same equation. This is variation number 1. This is variation number 2. And the third one is variation number 3. Log to the base E. E is known as the Euler's number. You know the relation between log to the base E and log to the base 10. Log to the base 10 is 2.30 times of log to the base E. So this is equation number 1. What does N stand for here? N stands for the number of nuclei at this time. What does N naught stand for here? It is the number of nuclei in the beginning of the process. So please note it down. Do not sit. I am seeing everyone sitting, and that is a big, big, big negative thing. You have to note this down. Note it down. What does N stand for? N stands for the number of active nuclei. What does N naught stand for? It is the number of initial nuclei. What does lambda stand for? Lambda is the decay constant. What does T stand for? T stands for time. And this E is your mathematical E. E is the Euler's number. Have you come across this Euler number in log? Yes or no?
Yes, sir.
That is a Euler's number, beta. You don't have to know what is the value of Euler's number. That is out of the course. You just have to remember the name of the symbols. Have you written this?
5 seconds.
5 seconds. I'll give you 5 seconds. Don't worry. Note this down. You have to note the the meaning of all the terms so that you don't get confused. If I ask you at any time what is the meaning of this term, how the equation is written, you should not get confused. If you get confused, it is a very big red sign. Have you written this, all the three forms of the equation? Can I have some raise hand that you've written this?
Done, sir.
Done, sir. Then, sir, again, equation number 3 gives us the number of active nuclei at any instant. So this N stands for the number of active nuclei. Yes or no? We understand this?
Yes, sir.
One more thing they can ask, how many nuclei has been decayed? What is the number that has decayed? Initial number is N naught. Right now the number is N. So if I subtract N from N naught, this is the number that is going to be decayed. So the number that has decayed is N naught multiplied by 1 minus e to the power minus lambda t. We understand this?
Yes, sir.
We will have to write this. Lambda is independent of the amount and time and any physical or chemical changes. It only depends on the nucleus which was there at the beginning. Lambda is also known as decay constant, disintegration constant, radioactive constant, Rutherford constant, steady constant, probability of decay per unit time. You can have various names for this. In the examination hall, they might not call it as lambda, as decay constant. They might call it by different names. Please don't get confused with the different names. We understand this?
Yes, sir.
Well done, sir. I don't see the same enthusiasm in today's class. Are you tired in today's class? Let me know. Is that so?
Yes, sir.
Why you are tired, sir? Tell me, sir. Did not woke up at the correct time. What is making you tired? I see everyone being tired. What is the reason? You had a party last night? What? Tell me.
No party, sir.
What, beta?
No party, sir.
Then why are you tired? Slept late? Studied hard? What? Woke up late?
Bad breakfast.
Bad breakfast. See, life cannot be defined by a single meal. I never got breakfast or lunch or dinner in my hostel time, and most of the time I was empty stomach. But that does not deter us from doing our activity. If a breakfast, a good or a bad one, every food that God has given us good, it cannot be bad. First of all, anyways, the taste may not be of your liking. That is a different case. Anyways, what I want to say, if a bad breakfast is so-called bad breakfast is making you miss a class, well, you are missing a very important time of your life which you are never going to get back, because this thing we are not going to study again. And if this same question comes in the examination hall, you will lose 5 marks, beta. Please be attentive. Okay, I'm just going to finish this class here, I mean with this theory part, so that in the next class we can deal with questions straight away and I don't have to spend time on question. This is a graph of time versus number of active nuclei. Do you see number of nuclei on the y-axis? Do you see this?
Yes, sir.
This is the time on the x-axis. Do you see this? And you can see an exponential curve. This is the number of active nuclei wala curve, and this is the number of nuclei which is decayed wala curve. Do we got this? Do we get this?
Yes, sir.
Then we have one time which is known as the half time, where the number of nucleus becomes half. Do we understand this?
Yes, sir.
Yes, sir. So, sir, draw this diagram, sir. And remember this diagram, sir, because the same diagram will come to you in the examination hall. Then at the examination hall, you cannot write because you have to fill bubbles or whatever. You cannot write, I had breakfast on the 29th of March 2022 and I did not attend the class, and that's why I leave 5 marks and I leave my entire college. Will you write that? No, na, sir. You will
No,
write it in the
sir.
examination hall and you will explain it to your dad. Why did you lose 5 marks? that day I did not enjoy breakfast. Good reason. Remember, failure has many reasons. Once you don't succeed in anything, which I don't ever imagine for you, that you will not succeed in anything that you try. You can give 1,000 reasons for your failure. Those 1,000 reasons may be valid, they may not be valid, but that does not change anything in your life. That time is gone. Those 1,000 reasons are not going to give you back that particular thing that you've lost. There's only one reason when you succeed, that you worked hard. That's it. Instead of 1,000, look for one. Work hard. That's the only way that can get you out. Do you understand this? Yes or no?
Yes, sir.
Bad breakfast? No, there's no bad breakfast. There are no free lunches. And then comes the next thing, which is known as Half-Life. What is Half-Life? Anyone understands Half-Life, right? You might have played a game on PS4 or previously on computer. Half-Life. Have you played Half-Life? Yes or no? Right? There was a game where this hero was going, and all these aliens were coming, and he was shooting. There was a very popular game when I was of your age, probably. Heard about this game, Half-Life?
No, sir.
No, sir. Your half-life is wasted, sir. Anyway, sir, right now you understand what is half-life. It is the time during which the number of active nuclei reduced to half of the initial value. Got this? To write this, at time
Yes,
t is
sir.
equal to 0, the number of active nucleus is and not. At time t is equal to H standing for half-life, the number of nuclei will be n by 2, n naught by 2. So this is the equation. These are the two equations that you must remember for half-life. This is equation number 1, and this is equation number 2. It is ln 2 by lambda. It is 0.693 by lambda, or approximately you can use as 0.7 by lambda. Remember this. Do not forget this. Back breakfast or no lunch or no dinner or fast or sabudana khichdi or utpam or rasam, your favorite maybe, doesn't change anything. The formula remains same. Do you understand this?
Yes, sir.
Write it down, sir, in your notebook, sir.
Okay, sir.
Please, sir. That will do a lot of what should I say? Help to me, sir, in your what I say. I'm not getting the correct word, sir. You see it on your board? N naught by 2 is n naught e to the power minus lambda into t half. From there, t half is ln 2 by lambda. ln 2 is 0.693 by lambda, or it is 0.7 by lambda. Have you written it?
Done, sir.
Okay. In this radioactivity wala chapter, there are only two things that are important that are going to come. One is the half-life. Half-life. You can search Google for half-life. You might find this topic. You will also find that game that I'm talking about, Half-Life. I was very big fan of that game. I killed all those aliens. I really loved it. Anyways, one is half-life. The other one is mean or average life. Now, this mean of average life is the average life of all active nucleus, how much they have lived. And this is the formula. There's nothing that you can understand in this formula. You just have to remember T half is TH, T average or T mean is TA. TH is 0.693 by lambda. We remember this, yes or no?
Yes, sir.
But T average is 1 divided by lambda. It's the inverse of lambda. Do we understand this?
Yes, sir.
At time t is equal to 0, the number of active nuclei is n naught. Then that at time t is equal to Ta, what is the number of active nuclei? It comes from this 37% of the original value. You cannot forget this in your life up till your NEET exam. Else this question will come and you will be at sea. How many number of nucleus are remaining? Is this one. How many have disintegrated? 37 are remaining, so 63% have disintegrated. Yes or no?
Yes, sir.
And this is, as you can see, it's written in bold letters. It is a very, 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 Very important relation. T average is 1 by lambda. This is T half divided by ln2. This is T half divided by 0.693. This is 1.44 times of TH. You cannot forget these relations because a straightaway question can come. You cannot waste time on that straightaway questions. Getting my point?
Yes, sir.
Sir.
You all understand this, bacha? Can I have some raise hand from all of you? That gives me more confidence that everyone is there with me.
Yes, sir.
Yes, sir. And
Yes,
sir, then sir, this sir, small point, sir. We will end the class on this note, sir. T half means 50% of nucleus have decayed and 50% are active. We understand this.
Yes, sir.
T
Yes, sir.
average means 63% of nucleus have decayed and only 37 remains. Do we understand this?
Sir.
Okay, sir. Then, sir, I will wind off the class here, sir. There was one more thing that I wanted to do, but I think I've given you enough for a day. And I must now resist myself in going any further. So, what are you going to do now? Obviously, you're waiting for your lunch because the lunch would be better than the whatever you got, right? Okay. So you go and have your lunch. But after
Okay.
lunch and before coming to class tomorrow, what are you going to do?
Revise the notes.
Revise notes, because if you come without revising notes, the entire class for tomorrow is going to be of no use. So if you don't
Yes.
revise notes, it's better that you stay at home and you have more breakfast.
Okay, sir.
Okay.
Okay, sir.
So don't have that. That was sarcastic. And real thing is, you have to come in your class after studying the notes of this class, because this encompasses everything that you have to study. On that note, I will wind off this class. I hope, apart from the breakfast, everything was good. And I'll see you tomorrow in the next class. Take care. Have a nice day.
Okay, sir. Bye, sir.
Bye.